It's a great pleasure to be here, but it's very intimidating after this stellar lineup. So I think I'm speaking here on behalf of the many anonymous physicists who are always enjoying Feynman's wonderful contributions. Now, I must say I'm being immunized a little bit by being intimidated. Freeman Dyson is always around, and you know that's sometimes an interesting experience. For instance, somebody made this wonderful tie for me with physics equations. And when I showed it to Freeman, he said, yes, I have a tie like that with E equals mc squared. It was made for Einstein, and Einstein gave it to me. So that's how it feels to be a younger physicist, I guess. I want to tell you a little bit, perhaps two different points of view. First of all, perhaps Feynman as an artist. I have some of his beautiful drawings behind me. And also about his mathematics. Now, as far as his art goes concerned, there's this kind of wonderful art critic in physics today who said, Feynman's art is at least as good as Rembrandt's physics. And I must say his bongo playing is so better than Mozart's physics. So all of this is a great liberation. If you think about the way he communicated, I think there are two ways in which we as human beings can communicate, which are roughly related to our left and the right-hand side of our brain. We can use words, and he was a master, the stories, the beautiful lectures, the logical order. And we can use images, pictures, that speak to us. And if you think about mathematics, which is really the language of nature, there are basically two ways to do mathematics. There is the algebraic approach, logical thinking, step by step. And you can think this kind of moving in time, causal series. Or you can think in terms of geometry, which is a visual experience, objects that you can move in space, you can walk around. It's much more something for our right hemisphere. Now, physics kind of use both, but the fundamental theory of physics are in some sense kind of split between a more abstract algebraic approach, which is quantum physics, typically how you learn it in physics courses, with very foreign concepts like imaginary numbers, Hilbert spaces, wave functions. And then there is more geometry in the realm of gravity and general relativity, space-time, space that can be curved, that can behave, that can move. And both of them are actually relevant for us. Now, Lenny already said that Feynman was a great connoisseur of mathematics, and of course a computational wizard. And I like this quote of him that he says, to those who do not know mathematics, it's difficult to get across a real feeling as to the beauty, the deepest beauty of nature. If you want to learn about nature, to appreciate nature, it's necessary to understand the language that she speaks in. Now, it's also known for the following quote, if all mathematics disappeared today, physics would be set back exactly 1 week. I felt this was like the perfect put down to mathematics until a rather famous mathematician gave me a good answer. He said, that was the week that God created the world. So I would say 1 to 1. But to understand this, a little bit kind of this image, how Feynman taught us to learn and to teach and to think and calculate basically with pictures. We have to do a little bit of space-time physics. So Einstein famously said that time is the fourth dimension. And some way to visualize this, here you see this little movie. It's two particles orbiting each other. Now think of that movie as a collection of pictures and stack the pictures on top of each other, like I'm doing here in this animation. You get a big stack of pictures where time is now in the vertical direction. Now if you glue all these pictures together to one big solid, these particles become strands, like spaghetti strands, that are floating through space-time. So this is the modern way in which physicists think about processes. There are these kind of world lines twirling through space-time. Now, in some sense, this line of thinking came in a very famous telephone call. It's actually described by Feynman in his Nobel lectures. So John Wheeler, who at Princeton was his thesis advisor, calls him up and says, Feynman, do you know why all electrons have the same charge and the same mass? It's kind of quite spectacular. Elementary particles are made perfect copies of each other. It's like there's a factory that builds electrons that doesn't make a single mistake. And then Wheeler said, I know the answer, because they're all the same electron. there's only one electron in the whole universe. And this was the image that he had. Here is the electron, it's sitting there, now it will float up in space-time. But suppose that that electron also was allowed to go back in time. If I was allowed to go back in time, I could, after my lecture, step in a time machine and re-enter the stage and stand here next to me. It would be an identical copy of myself. And in fact, I could do that many, many different times. So if that electron could weave a big knot in space-time, and you would cut it in slices, in a series of pictures, on the first picture would only be one electron, but in the middle you would have many electrons, and particles going back in time, which are anti-electrons or positrons. Now, Feynman immediately remarks, well, if that's the case, there should be as many electrons as positrons, and of course there aren't. But that picture was in some sense the birth of the path integral, of Feynman diagrams, all the techniques that we now use in physics all the time. This is a page of his notebook, and I find it very touching. But for the first time, he's sending these particles back in time. You see, they make little loops, and he's computing, and it kind of all works out. And I would say the rest is history. The diagrams, the Feynman diagrams, took over. There's a famous episode where Feynman is kind of speculating that in the future, physics books will not be just text and formulas, but they will contain all kinds of pictures. They would be more like cartoon books. And of course, that's true now. If you read physics journals, physics papers, there are diagrams all over, not just equations. And that actually set physics free. I mean, it's very important to understand that this actually led to all the future developments that we are now in the midst of. String theory, for instance, would be impossible if we weren't able to generalize the Feynman diagrams to two-dimensional surfaces, again, of all kinds of different shapes. Mathematicians are using these techniques. For instance, they can make these world lines and build knots out of them. And they can calculate using the rules of physics. So also in mathematics, Feynman diagrams are everywhere. In fact, even in fundamental theories that theorists are now thinking about, like quantum gravity, they still use the fact that we think of it in terms of geometrical shapes. Even space itself can change and move. Now, there's a great episode that Feynman describes when he basically makes the fundamental discovery that there are two ways to think about quantum mechanics. There's the traditional way in terms of operators and states, and there's his new way in terms of these kind of spaghetti strands. The sum over all paths, the sum of all histories, is a complete radical reformulation of quantum mechanics. And it's so important in science that there are people who are able in some sense to take the field and make it a 90-degree turn so that we have a completely different and fresh view of something that we already knew. And Feynman describes his looks into the literature. Somebody points him to a paper by Dirac, who says that these two approaches are, in a very elementary form in Dirac's equations, are analogous. And Feynman asks, what does it mean, analogous? And he said, well, and the person who pointed out says, you Americans, you all want to have a use for everything. Well, Feynman says, well, perhaps he meant equal. And that's kind of a tremendous moment. He puts the equal sign, and the two different views become one. I'm not going to bore you with equations, but a typical mathematical equation looks like this. A equals B. And we've spent a lot of time in our courses to explain what A and B is. But actually the simple symbol in the middle, the equal sign, is as important. Because a good equation will connect two worlds, A and B, that are completely different. And the two strands of the equal sign allow information to flow in both directions. Einstein was famous in writing these beautiful equations, like equals mc squared. But Feynman was too. And that's the magic of his contribution. Now, he had a tremendous impact on mathematics, but he didn't really like mathematics. For instance, in 1966, John Wheeler invites Feynman to a conference to bring mathematics and physics together, and he has a very long letter outlining what the program is. The answer of Feynman is very brief. Essentially, he says, I'm not interested in what today's mathematicians find interesting. End of the story. I must say, by the way, also, I heard from another famous mathematician that he was in a lecture of Feynman where he was explaining to mathematicians how they should prove their theorems. And this mathematician said, well, they don't make physicists like Dirac and Pauli anymore. But what we are confronted with here, that sometimes in science there are different points of view, and you have to kind of choose. You either have to have the wonderful physical intuition that he has, or you have the mathematical rigor to prove theorems. And sometimes they simply do not go together. It's very different to combine these 2 points of view. It reminds me a little bit like Heisenberg's uncertainty principle. You know, an electron can sometimes be a particle and sometimes can be a wave. Now, when Heisenberg discovered this, actually he wrote this to his friend Wolfgang Pauli, and he wrote back 2 weeks after the discovery, basically, of modern quantum mechanics. And Pauli says, oh, I think I understand what you mean. If I open my left eye, I see a particle. If I open my right eye, I see a wave. If I open both eyes, I become crazy. Very few people can open both eyes together. And I would say Richard Feynman was one such person who could combine the left and the right side of his brain. One simple illustration is another exotic phenomenon that should be mentioned. Feynman is a very famous case of somebody who has synesthesia. For those of you who don't know what it is, it's the affliction that you see colors when you see letters or numbers. I actually have it myself, and for me it was a great relief to read that I was not the only one, that this famous physicist had it too. And you know when somebody has synesthesia, if you see that the colors are described in great detail, so like third decimal precision. Like the N is slightly violet, bluish for Feynman. For me, it's actually dark green, so it's completely wrong. But I think actually there's some theory about psychologists, what synesthesia means. Clearly, it means that the compartments between your senses are not watertight. There's leakage. You're kind of using several senses at the same time. And I think actually for me, it's in some sense the magic of Richard Feynman, that was able to take all these different points of view together. His physics, his mathematics, his art, his music, his love for life, and they were all connected. As he writes here about his drawings, he made the drawings as an appreciation of mathematical beauty of nature, of how she works inside. It's a feeling of awe, of scientific awe, which he felt could be communicated. Sometimes through a drawing, sometimes through equations, sometimes through a joke. So what's for me the lesson of this celebration? Well, first of all, I think it's the tremendous impact that exceptional people have, and how important it is to celebrate that. But for me also, I think we should all be aware there are many, many, many Feynmans around the world, both Richards and Jones. And they need to be discovered. They have to be taught. They have to be inspired. There must be places like Caltech that can host them and make them bloom, and I think so that they, again, can inspire next generations. And I think actually that's the great lesson of Richard Feynman. Thank you very much.